Alright, so I tried to get my wife to bring Sadie for the beginning of the review session, but she said she has a coupon at the loft that's going to expire. So she and I have different priorities, I guess. Alright, so another time we'll get that worked out. Alright, so I think I might have an inner ear infection, so if I like fall over while I'm talking, well, make sure I don't hit my head. I'm just a little, it's dizzy. I don't know, I feel very foggy. Anyway, so here we are. It is the day before the exam. Blackboard is coming through, like usual. Hopefully everyone has access to Blackboard now, or at least to your classes now. Does anyone not have Blackboard access at this point? Yeah, it seems like that's working fine now. So you can imagine I got bombarded by emails this morning regarding that. So that's up and working, and so really all we've got left is just to maybe talk about a few things, and then we will head into the exam tomorrow. And so, this is generally a very student-led conversation, but I will go ahead and preface it and try to maybe pull out any questions, like general questions, format-wise, anything you might have, and I can answer. I will try to. So any of those types of questions? Yeah.
So when you said before that you were shortening or making more short answers on a test like this, would that mean there would only be one longer response, or?
So that means, so if we look at this exam, so this is the 2015 exam. The third and fourth page, so the third page is calculations, the fourth page is a Lewis structure problem. Honestly, in the end, it's not too different. I have limited the calculations, just like this one, to one page. So it's, format-wise, I think, going to be, and it ended up being more similar to this than maybe I had thought of previously. So, yeah. Yes? Yeah, so I don't think time should be an issue. That's always my biggest fear, is that I make the exam too long. I don't expect time to be an issue. I'm generally lenient with time, and then I'm a total hard ass with time. So what that means is that at 50 minutes, I'm not going to come rip it from your hands. At 55 minutes, and I will have a clock, at 55 minutes, if it is not in my hands or in the box, I will take points off of your exam. So I will give you as much time as possible, and then after you've exceeded the 5-minute overtime period, I will literally take points off your exam, and I will announce that at the beginning of class tomorrow. So I'm fairly lenient, I think. And the only reason I'm like that with the timing is I got another class. Like if you're the 11 o'clock class, I've got another class I've got to get started literally in 5 minutes at that point. So it's just a matter of getting turnover. So yeah, I don't care too much about the 50-minute timing, but don't push me on 55. Yeah. Yes.
Can you explain the abundance of with the lithium, why Li7 is more abundant than Li6 or lithium 6?
So yeah, with that problem, it says that, it's asking you to, it's a greater than, equal than, less than question. It says lithium occurs naturally as lithium-6 and lithium-7. The relative abundance of lithium-7 is what compared to that of lithium-6? So what information do we need to, I guess, answer that question?
The mass at the bottom of the periodic table.
Yeah, so we look up here at the atomic mass of lithium, and we can see that the atomic mass, which of course the number on the periodic table is a weighted average that takes into consideration the abundance of specific isotopes. And so here, we can see that we've got a number of 6.939. All right, so if our number on the periodic table says 6.939, what does that tell us about the relative abundances of lithium-7 and lithium-6? Which must there be more of? Yeah, and it's just because the weighted average then skews very close to 7, and so that atomic mass is saying, well, while lithium exists as both lithium-6 and lithium-7, it's like almost all lithium-7. There's a little bit of lithium-6, which is why we look up here and the number isn't just 7.000, right? So there's a little lithium-6 which skews it down, skews the weighted average down below 6, but overall there's a lot more 7 than there is 6. So I guess the answer here would be greater than. Yeah.
The first question on this little, on the table right there, the energy required from an electron from n equals 1 to n equals 5. Can you go over, I guess, kind of what, I'm just struggling because I don't really know like what it's asking.
Yeah.
And how it applies.
I like this one a lot, and it's not, you don't have to do math, it's really just a conceptual question. And so we've got two processes going on. Now first off, what is the ionization energy of an atom? It's the amount of energy required to do what? Remove an electron. And so does that mean take an electron and move it a little higher in energy, or does that mean just strip the electron completely off of the atom to the other side of the room? It's the second one, right? So it means completely removing that electron from the atom. Okay, so what we've got are two different situations. So we've got one situation where we have some atom, I guess it's hydrogen. And so we're saying that we're going to remote an electron from n equals 1 to n equals 5. And so we've seen that in the Bohr model of the atom, we can actually we can model these things as being actual discrete orbitals, and that works out fine because there's only one electron in hydrogen. And so we'd say, well, what we've got is n equals 1 here, and up here we've got n equals 5. And so the amount of energy required to promote it from n equals 1 to n equals 5 is going to be this delta E, which basically spans from n equals 1 to n equals 5, right? So if we excite an electron, we're moving it away from the center of the nucleus, and so we're going to have to put energy in because, again, it's like pulling apart a magnet, right?
Yeah.
How far we pull it apart dictates how much energy it takes. So it's just going to take a little bit of energy to just pull it a little, right? Say go from 1 to 2. To go from 1 to 5 is going to take a lot more because we've got to keep pulling all the way up to 5. And then if we're talking about ionization energy, we're saying that we're taking that magnet, I'm going to take one of it and just throw it to the other side of the room, meaning I'm going to completely remove it from the influence of the proton. And so would we expect that, the throwing the electron across the room, to be greater delta E or smaller delta E than that? It would be greater, right? Because basically what we're doing is instead of taking that electron here and promoting it to n equals 5, we're taking that electron and we're promoting it all the way up, wherever there stops being any distinguishing difference between energy levels. Once it can no longer fill the pull of the proton. And so what we would say here is that the energy required to promote an electron from n equals 1 to n equals 5 would be less than the ionization energy. And again, that's just testing the concept. But what does ionization energy really mean? And it's just basically it's exciting an electron so high that it just leaves the atom. Yeah.
Why is for the second one gamma radiation less than atom?
So, were there any other questions about the one we just did? I'll come back to yours, and then I like to just kind of get top right on it. Yeah.
Is the 1513 whole deionization?
Yeah. And so that's kind of like a red herring there. You don't need the value. You don't need to know anything about the value. The important thing is just actually knowing what the ionization energy is. Other questions about that one? All right. So then the second one. It says the wavelength of gamma radiation is compared to, or is greater than or less than that of infrared light. And so let's see, we've got, I can't remember how to draw gamma, so I'll just write gamma. We've got gamma and we've got IR. And so which is higher in energy? It's gamma. So here we've got high energy, here we've got low energy. Now what's the relationship between frequency and energy? High energy has what kind of frequency? High frequency, right? That means it's beating a lot. So the faster our wave is waving, that's going to have higher energy. And so we've got high energy. Light is going to have high frequency light, and that means that low energy light will have low frequency. Of course, this question is asking us about the wavelength. And so we know that when we compare wavelength and frequency, we say that we can say that C equals the frequency times the wavelength. And so C, of course, is a constant, right? And so on this end, as we're increasing our energy, as we're going towards the gamma radiation, we're making this number bigger. But over here, since we've got a constant, what must be happening to the wavelength? It's got to keep getting smaller, right? And so that's that inverse relationship between frequency and wavelength. And so over here, gamma radiation is going to have a low wavelength. IR radiation would have a high wavelength. And so the thing to keep in mind is that all this light is traveling at the same velocity, and so that means it's traveling across. If it's waving very slowly, it's going to have these huge gaps between crests, right? And so it's low energy light, and there's huge gaps between crests. Going the other direction, if we have gamma radiation, very high energy, it's beating very fast, it's going up, down, up, down, up, down, and so the distance between those crests of the wave are very close together. And so in fact, high energy light will have very, very short wavelengths. Yeah.
In terms of like the last question, could you talk about just what we talked about last class, how like more bonds results in smaller bond length?
Yeah, and so here it's just the big trend to know is that as bond order goes up, we're going to see bond length go down. And so the higher our bond order, meaning once we start adding multiple bonds, that's going to make our bond stronger, and that's also going to make our bond shorter. And so in this case, we're talking about the length of a CN versus the length of a C double N, or I guess C double bond to N. And so since the C double bond to N is stronger, that's going to make it shorter. And so we would say that the length of a CN bond is longer than that of a C double bond to nitrogen. I feel like I'm on a cloud up here. Yeah.
So for the one that's the radius of S2 minus and Cl, if you add an electron, it doesn't have any effect on the radius?
It does. So as it comes to ionic radius, certainly if we're talking about a Cl minus and a Br minus, those are, which would you expect to be the bigger ion? You expect Br minus just because it has electrons in a higher valence shell. But it turns out the difference in size between ions of the same charge, it's not that big of a difference. Where we do see a huge difference in ion size is once we have different charges. And so what happens is, and remember in class I told you can kind of think of this as a tug of war. So you've got your atom size, and at this point, as we think of size, it basically comes down to do we have more protons or more electrons. And so in this case where we have a minus charge, we have one more electron than proton, so they're going to win the tug of war, which means this thing's going to get bigger. And then as we add a second electron, what's going to happen? It's going to get even bigger. And so that charge difference is actually really significant, and in general is going to be more important than any of the size trends going left, right, or up and down. It's really just going to come down to charge. And so in this case we have an S2 minus versus that of a Cl minus. And so we would definitely expect the S2 minus to be greater because the electrons are winning that tug of war more. So we would say greater than. Yeah.
I have a question more about the exam in general. What formulas and constants are going to be provided in the exam, or is it just going to be provided based off the equation? Like, are we going to have a Planck's constant?
So I've got the cover sheet up under the kind of the exams folder, and so that's the exact cover sheet you'll see tomorrow. I give you constants like Planck's constant, speed of light, stuff like that. I'm sure I give you Avogadro's number, and then there's a periodic table and most of the formulas we've seen. So just check that out. Yeah. Yeah.
If there was a question on polarity, you would give us the electronegativity, right? What do we need that to determine where it fits in that trend?
If there's a question on bond polarity, you're going to be able to figure that out based on the electronegativity trends of the periodic table. So I'm not going to give you electronegativity values, but you should know if we're looking at, say, a phosphorus nitrogen bond versus a phosphorus oxygen bond, which would be more polar. Phosphorus oxygen is because oxygen, we're not changing the phosphorus, but we are making the oxygen more electronegative, which is going to make it more polar. Yeah. Yes.
Okay,
Yeah.
sorry. What's the difference really between electronegativity and electron affinity?
Yeah, that's a good question. Those are two things that are easily mixed up but are 100% not the same thing. And so electron affinity is by definition is going to be the amount of energy that is released when we add an electron to an atom. And so it very much has to do with like ionizing to a negative ion. It's not going to have anything to do with covalent bonding. So then when we talk about electronegativity, electronegativity is much more of a covalent bonding concept. And so by definition, what it is it's more or less the electron greediness of an atom that is involved in a covalent bond specifically. And so really, we've got electronegativity describing, you know, how much an atom wants an electron in a covalent bond, and then you've got electron affinity describing how much an atom wants an electron in an ion bond. And generally, we see the trends are similar, right? We see that fluorine is the most electronegative atom, and I think it also has the highest electron affinity. And so they go hand in hand, but the values aren't the same. They're different definitions. And I think generally, with electron affinity, if you look at the periodic table of electron affinities, there's not nearly the nice, neat trend. You see that there's some kind of increases and decreases in electron affinity. So that's why I kind of boiled that down to one of the tables. These are the ones, the halogens have big electron affinity. Column 6 is moderate and everything else. Yes?
Over the past 4 weeks, we've seen like a few equations that have the Rydberg constant in it.
Yeah.
But one of them, like one is 1 over lambda, the other one was energy.
Okay.
But for both equations, like I think the Ni and the Nf are like switched in the equation.
Okay.
Can you just go? Can you just both of those? Which one is?
Yeah, I mean, I tell you, the easy way to remember that, and you don't even need to remember which comes first. You're going to subtract 2 fractions. You know, you're going to subtract 1 fraction from another, and whatever you do, you want to end up with a positive value. Okay. All right, and so what that means is if you've got, say, you know that there's a transition of 3 to 2, but you can't remember if you subtract a third from a half or a half from a third. Well, you need to end up with a positive value because, for example, you can't have a negative wavelength. That doesn't make any sense whatsoever. And so here what you'd have to make sure is you'd say, well, I know that if I subtract 1/3 from minus 1/2, I'll end up with a positive number. And so that's how you would do it. Yeah. Yeah. Amy.
For the electronegativity of hydrogen, like, can you explain how that fits into the ground? It's like ionic versus covalent. Like, because I've seen it in both, but like.
So, you know, I'm comfortable going out on a limb and saying hydrogen is never really involved in ionic bonding, even though you'll sometimes see people write, they'll shorthand acid to be H+, indicating that that very much looks like an ion, right? But H+ very much does not exist. What that's really representing is, this would be acid in solution. That's representing hydronium, which is basically a water molecule that's had a hydrogen added to it. And so H+, though, it's not so much a thing. So hydrogen really only does covalent bonding. So even when you see it written like this, it's really indicating that it's involved in the covalent bond. Yeah?
This is kind of conceptual, but when we're talking about like fluid structures and we can do electrons first, and then we like end up moving them around to create, like to make things closed shell. Since we're moving around electrons and some atoms are getting more valence electrons than they want, how is that not ionic?
So what we're doing is totally not what's going on in real life. So what we're doing is we are taking these neutral atoms, we are stripping the electrons away, connecting them like an erector set, and then adding the electrons back as we see fit that makes sense. And so the true nature of covalent bonding is, you know, maybe not surprisingly, is way more complicated than what we've talked about this far in general chemistry. And so what that is it's a tool that actually allows us to model the electrons using dots and sticks, right? It works really well, and it's actually a really good representation of how the electrons are distributed in a molecule. But of course, when these molecules are bonding together, they're not saying, well, here, let's take off all of our electrons and, you know, come over here and connect together and then put them. All right. So that sounds almost R-rated, but yeah, it's a make-believe thing. That's not what happens when they come together. And so that's just something that we can do, and we end up at the right answer, and it's pretty fast and easy. just like a general concept.
Does it depend on cation?
Yeah, so it both. And so what we're going to see is, as far as lattice energy goes, which of course, remember that, so just generally speaking, lattice energy is the energy that is released when two ions come together and form a really nice tight crystal lattice. And so we talked about two trends, and so those two trends, as far as determining which is going to have, which ionic compound would have greater or less than, for a lattice energy, we've got charge, and then we've got ion size. And so generally I will say charge is more important. Charge, if we have, say, a sodium plus ion versus a magnesium 2 plus ion, that magnesium, 2 plus ion is going to be a lot harder to pull apart because we have to remove, say, 2 chloride ions from it, and that's just a lot of energy, right? We're leaving something with a +2 charge, and the more charge we have, the higher an energy is, and so we've got to make up a lot of lattice energy. So, for example, we would expect MgCl2 to have a greater lattice energy than NaCl, and it's all about that charge of the magnesium. And really, we're just focusing on the cation in this case, but you would expect a similar trend for something that has, say, like an O2 minus charge. I'm trying to think of an example. So let's say we were comparing I don't know if this is a real thing, but potassium oxide, so K2O, with, let's see, we'll compare that with KCl. Okay, and so in this case, what we've got is, we're not going to compare the potassiums because each potassium is providing a plus charge, just like the chlorines are providing a minus charge here. So there's no difference there. And so then what we look at is we know that the chlorine definitely is going to have a -1 charge. And then oxide, oxygen has what kind of net charge ionically? -2, and so again we see the greater charge, and so I don't know if this is true, but the trend based off of what we've learned in class would say that this would have the greater lattice energy because there's something with a higher charge involved. And so if there's higher charge, that means things are just sticking together a lot more tightly. Then you've got ion size, and so that pretty much is just going to follow, the trend. It's not nearly as important as the charge or the amount of charge, but for example, you could have, say, sodium chloride versus lithium chloride. And so we've got a situation where the way that size has to play a role here is the smaller our ion, the more intimately we can pack our crystal together. And so the more closely everything's packed together, the harder it's going to be to rip apart, meaning closer things packed together will have a greater lattice energy. And so we can't really do anything with the chloride here, but we can compare the sodium and the lithium. And so which one is smaller and would provide for a more intimately packed crystal? Definitely lithium, and so which would have the greater lattice energy? Definitely lithium chloride versus sodium chloride. So that would be our trend there. So yeah, that's kind of the two things that you should be cognizant of.
Would transition metals fit with these trends? Or?
Yeah, I mean, they might start to do some wonky things, but as far as we're concerned, if we saw, say, like an iron 3 chloride, we would expect that to have a greater lattice energy than a magnesium chloride for the same exact reason as we talked about. So, yes.
Can you briefly go over the general periodic trends you want us to know, just like which things we did?
Yeah. So you might have to help me remember what we've got. So first off, there's atom size, and so we can actually write these down. Let's do that. All right. So we're just talking about periodic trends. And so for periodic trends, we've got atom size. And so that we would say, that's a funny looking Z. As far as atom size is increasing, we'll do everything increasing. All right, so where are we increasing in atom size? Are we increasing up or down the periodic table? Down, because we have a greater principal quantum number with each row. And then are we increasing left or right? Left. Right? Yeah, correct. And so, yes, we are increasing to the left. And the reason for that, of course, is as we move to the right, we have more protons that are going to just keep sucking in our electrons closer and closer and closer. And so we start out with pretty big lithium. And so as we move across the periodic table, things get smaller and smaller and smaller and smaller until we move down to sodium. And so we go up in principal quantum number. And so now we're going to have we're going to be big again. And then as we add more protons and more electrons each time, we're going to sink in a little closer and closer every time. All right, so atom size increases down and to the left. Let's see, so then we've got ionization energy. And so essentially, of course, ionization energy is a measure of how difficult it is to remove the outermost electron in an atom. And so is that going to increase with electrons far away or close to the nucleus? What's going to be harder to remove? Close, right? Because they're more intimately connected. And so up and down the periodic table, will it increase up or down? Up, because our atoms are getting smaller, and so those valence electrons are closer to the nucleus. So it's increasing up, and then left or right, is it going to increase or decrease? Well, it's just another size argument, more or less. And so our atoms getting bigger or smaller as we go to the right? Smaller, and so our electrons are getting closer, and so again, it's going to be harder to remove those, and so it will increase as we go to the right. All right, so then we've got electron affinity, and so that's a measure of the energy released when an atom gains an electron. And so, you know, it's hard to even put a trend here, and so I don't even worry too much about it. I just say that halogens, we did this in the notes, halogens high, column 6, moderate, and that's about it. There's not a very neat trend as far as electron affinities go for reasons beyond the scope of this class, but the things that really want to gain an electron that we would expect for that to be the case, halogens that need 1 electron to be closed shell, they have very high electron affinities, and so we see a lot of energy released. And then there's the somewhat related, but definitely not the same thing, electronegativity. And so electronegativity is going to increase up or down. The easy way to remember this, what's the most electronegative element? Fluorine. And so is fluorine at the top or the bottom? It's at the top. So we're going to increase up. And then are we going to increase to the left or the right? Yeah, to the right. Are there any other ones? So we did lattice energy, and we saw that kind of it wasn't so much a periodic trend as it was more like a think about the charge or the size. Anything else?
Radius.
Yeah, but that's what I meant with like atom size. So that's just atom radius is a measure of atomic size. Yeah, I think that's it. Yeah.
So I know you said that like electron affinity is kind of like not a big trend, but like in one of the practice problems it talked about like the relationship between ionization energy and electron affinity. And I was kind of like confused by your explanation. Is like a good way to put this about
So yeah, so let's say we want to make salt, and so we've got sodium and we've got chloride, and so what we want to make is sodium chloride. Now what we end up seeing is the case where we see a situation where sodium, to remove an electron to make sodium plus, has a delta E, which is really just the ionization energy, so we could say EI. And so you've got this in the note, so this is going to be rough values. I'll say somewhere around plus 400. So I don't know if that's anywhere close to right, but you can look that up yourselves. So then we've got chlorine, and so at the same time we know that ultimately to make sodium chloride we've got Na plus and Cl minus, and so what we find is the electron affinity of chlorine is pretty high. Is it going to be a positive or a negative number? Do we have to force the electron in there, or does that want to happen on its own? It'll happen on its own, just like, you know, a spaceship is going to fall to Earth. And so what we've got in this case, we could say that the electron affinity is roughly minus 300 kilojoules per mole. Don't have the values off the top of my head. And so what we've got is a case where, well, if we add up this energy, we end up seeing that the delta E for this process, is it greater than or less than 0? Yeah, it's greater than 0. It's a positive number. And so is there any reason for uphill processes to occur on their own? No, there's not. And so what ultimately is the reason that we do see sodium chloride form? That's the lattice energy. And so once we form our ions, then we have all that energy released from the ions forming these really tight connections with each other. And so ionization energy and electron affinity are kind of opposites in terms of whether we're removing or we're adding an electron. And then in addition to this, we must have lattice energy. What letter do we use for lattice energy? U. So we must have U to make this downhill. And in fact, would we say that as we're forming a salt, is the process going to be U or is it going to be negative U? Yeah, it's actually going to be negative U because we define lattice energy as the amount of energy it takes to pull things apart. And so then when we're actually forming the salt, it's the other direction. And so technically, we'd say it must be negative U because we end up seeing that U itself is a positive value. And so that's not exactly going to make it down. Yeah.
You got a walkthrough number 7.
Yeah. Number 7. Okay, so following this expression, calculate wavelength of light needed to ionize an atom. So you're given the Rydberg constant. You're told that Z effective is the effective nuclear charge for the element being ionized, and N is the principal quantum number. Okay, so you're supposed to solve for the wave. Hold on, what are you supposed to solve for? Yeah, you're supposed to solve for the wavelength. And so as we try to solve for the wavelength, we'll go ahead and write it down. So we've got wavelength is equal, no, wait, we're solving for Z effective. Okay, hold on. So we are solving for Z effective. So if we flip this thing around a little bit, we've got Z effective is equal to N squared over the Rydberg constant and the wavelength associated with the ionization energy. Okay, so let's see, we've got Z effective that we're solving for, N squared. So we're told that N is the principal quantum number of the electron being removed from the atom. So we're talking about lithium. So what is the principal quantum number of the outermost electron in lithium? Yeah, so it's essentially the question is what row of the periodic table is lithium in? And so it is in fact 2. So essentially we've got 2 squared times the Rydberg constant. And then we've got to come up with a wavelength of light. Now, unfortunately, we're not given the wavelength of light, but we are given the ionization energy of lithium itself. And so do we know any way to solve for, say, the wavelength of light associated with a process with energy 520 kilojoules per mole? Sure, so what is that equation? Yeah, so we can say, so the way that we learned it, we said it was H times C over wavelength. And so if we rearrange that, its wavelength, lambda, is equal to Planck's constant times the speed of light over energy. Now, when we talk about this equation right here, the energy, what are the units of energy associated here? Yeah, it's not kilojoules per mole, it's just joules per photon. So it's the SI unit for energy, which is joules, and then it's just per photon. So would we expect that energy to be really big or really small? Really small, and generally I think those are on the order of magnitude of like 10 to the minus 20th joules. So it's going to be a very small value, the energy that we get from this sort of equation, which means the energy we put in over here to solve for the wavelength also needs to be very small. Okay, so to figure that out, we've got 520 kilojoules per mole. And so, of course, how many joules in a kilojoule? Yeah, so in 1 kilojoule, we have 1,000 joules, and then we don't need it in per mole, we need it in per photon, so we'd say that in 1 mole of photons, there are how many photons? Yeah, so we'd say there are Avogadro's number of photons. And so what this is going to do is ultimately give us the E that we're going to spit into our equation above. Okay, so I don't have a calculator, otherwise I'd write these out, but you should be able to figure it out based on what we're doing here. So now we've got energy, and so specifically, we've got energies in joule per photon, or you'll just see that written as joule. I like to say joule per photon just to help us keep in mind that it is per individual photon, so it's going to be a really, really small value. All right, so we've got energy in joule per photon, and so we can go ahead and plug this in up here. Now, the thing to keep in mind that we're going to get some value here. What will the units of that value be? Well, it depends on what we use for the speed of light. And so generally, what units do we use for speed of light? Meters per second. And so if we're using meters per second for the speed of light, what are we going to end up with over here? Meters. And so specifically, we're going to end up with some value in meters. And of course, if we go back over here to the Rydberg constant, what are the units of that Rydberg constant? Yeah, specifically it is inverse nanometers. And so once we've got the wavelength in meters, can we just simply plug it in up here and do the math? No, so at this point we're going to have to take this value. It's that value that we'll put it in here, but we're going to have to make sure that we convert our wavelength to nanometers. How many nanometers are there in a meter? Yeah, so 1 meter equals 10 to the 9th nanometers. And so it's an interesting problem. Essentially, you're given the formula, and so it's up to you to figure out how we can manipulate the data. And so at the end of the day, what we're doing is we're saying, well, we're removing an electron. That's going to take some amount of energy. And so that amount of energy will correspond to a specific wavelength of light. So we can solve for that wavelength of light here after we convert the 520 kilojoules into joules per photon. That'll give us the wavelength in meters. We turn that into nanometers, and then we just plug it in. Remember, we got 2 from the fact, and so you're told in the problem that the N corresponds to the principal quantum number of the outermost electron in lithium, and so that's going to be 2. You're given the Rydberg constant. And so you end up with Z effective, I think, is in this problem somewhere around 1.58. Okay, so what is Z for lithium? Yeah, so we know that Z for lithium is simply 3 because remember, Z is just the atomic number, right? We had Z is the atomic number, A is the atomic mass. And so let's see what that really means, because I love how this kind of connects, well, because you might even wonder, why do we say Z for atomic mass? Remember, Z is really what we refer to as Z actual, and so it's what we would expect the outermost electron to fill being pulled into the nucleus, right? There are 3 protons in the nucleus. We expect this outermost electron to fill the pull of 3 protons. But what's going on between the outermost electron and the protons that maybe changes things up a little bit? Shielding, right? And so we've got inner electrons that are going to sort of be in the way between the protons and the outermost electron. And so because there's shielding taking place, would we expect the outermost electrons to fill a pull greater than 3, equal than 3, less than 3? Less than 3, right? So it fills that pull of the 3 protons, but at the same time, it fills the repulsion of the inner electrons. And so it fills the pull. It has a Z effective that is less than 3. And so that's ultimately what we're calculating here is, so, well, how tightly do those outer electrons really fill the pull of the nucleus? It's less than 3, which we might expect, because there's inner electrons that are shielding it from feeling the full effect of the nucleus. And so we end up with a Z effective that is less than 3. So we would say less here. Less than. Yeah?
Could we go over the trend for shielding again, or is that?
Yeah. So as far as shielding goes, what happens, the way to think about this is as we move across the periodic table, so let's say as we go right across the periodic table, what are we doing? What are we adding each time? Let's say when we go from boron to carbon, what have we added to the atom? Yeah, so we've added 1 proton, and then we've added 1 electron, and specifically if we added an inner electron or a valence electron. It's valence. And so specifically it's 1, it's 1. What have we done to the number of inner electrons? Nothing, right? It's still got the same number of inner electrons. So we'd say that there's no change in inner electrons. Well, no change in inner electrons. And this is ultimately why we see the periodic trend of atomic size that we do. So as what we're doing is we're adding a proton and we're adding an electron, which is out here. Are we doing anything to the shielding? What electrons provide the shielding effect? It's the inner electron. So we're not changing the amount of shielding that goes on, but what we're doing is we're having, basically we're adding a proton, which means that out here the electrons are going to feel a greater pull, and since we're not adding any shielding electrons, well, we don't even have to factor that in because there's no extra shielding going on. So as we move left to right, we're basically going to have more protons and more electrons that are attracted to each other, and we get smaller and smaller and smaller. It's just, we end up seeing our atom be a little bigger than expected because we do in fact have shielding going on, which makes the actual pull of these outer electrons not quite as much. And so the shielding happens, so they go a little further out because they just aren't as attracted to the nucleus as we might expect. The big thing to remember going left to right is just, again, we're adding an electron, we're adding a proton, and so they're more attracted to each other and we get smaller as we go left to right across the periodic table. Other questions about this stuff? Yeah? I cannot imagine off the top of my head a situation where it would be greater than Z. Because ultimately we're always, once you get past the first row, we're always going to have inner electrons that can do some sort of shielding. And so, it explains why, we've already said that as we go, as our angular momentum quantum number, which defines if we've got an S, a P, a D, or an F, and it goes on, there are theoretical orbitals like G and H that aren't actually filled in atoms. So what we've got is a situation where all the S orbitals are pretty close to the nucleus, the P's get further away, the D's get further away, the F's get even further away, and so that's why, ultimately, this row, what subshell is this? How would you define that subshell? It's the 4F. Which row is it in? It's in the 6th row, right? So 58 comes right after 57 here. The reason is that F orbitals are so far away, just naturally so far away from the nucleus, that they are shielded a ton. And because they're shielded a ton, they move a huge distance much further from the nucleus, which puts them way higher in energy, and so we don't actually start filling them until we get to the 6th row. Right? So, and that's ultimately just a shielding thing. So yeah, I cannot imagine a situation. I'm trying to think if there's any I don't think so. Maybe there's some weird trends with ions, but beyond the scope of this course. Yeah.
Can you talk about the magnetic quantum numbers and nodes again, real quick?
Yeah, and so as far as nodes go, we say that the total number of nodes is what? It's n minus 1. So that goes for any orbital. The total number of nodes is going to be n minus 1. And then we've got the total number of angular nodes. And so what does that equal to? L. And so what's the other type of node that's possible? Radial. So then we've got radial nodes. How do we figure out radial nodes? Yeah, we're pretty much going to take our total number of nodes, subtract away the angular, and whatever's left must be radial, because that's the two types of nodes that we have. So, for example, let's talk about let's do 5F. 5F doesn't get a lot of love. All right, so 5F, what's the principal quantum number of a 5F orbital? 5, and so how many total orbitals does it have? I'm sorry, nodes. 4, right? So we've got total nodes for a 5F orbital will be 4. And then what is L for a 5F orbital? So what is L for an S orbital? 0. P? 1. Forgot what's in D? 2. And then F is 3. And so L equals 3, which means that the number of angular nodes is what? 3. And then the radial nodes must be what? 1. I didn't get that backwards, did I, right? Okay. I've been known to do that in the past. Yeah.
LFL is everything equal to LFL.
Yeah, so what you've got then the question is, well, why do we have the number of f orbitals that we have? And that's dependent on m sub l. And so if L equals 3, how many possible values of m sub L are there? 7, because we've got 0. Yeah, so you'd have 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. Yeah, so that's why we have 7 f orbitals. Let's see, if we count here, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 electrons fitting into 7 orbitals. So that's why we see 14 down there. Yeah. Yeah. No, the experimental, let me make sure that's true. So the question was, do we need to know any of the experiments and things? I don't think so. I just love history. And so at the beginning of the class, I like to talk about some of that stuff. And I don't think you can really even talk about the atom without understanding how we got to where we got. So, but no, I'm not going to be like, what did J.J. Thomson's experiment tell us, and when was he born? That's not going to be on the exam. So. Yeah.
I know this is going back, but just on the Z effective stuff, like if you're looking at it as a trend, Z effective increases that way, but like the shielding increases to the left, right?
So I think what you would say is that Z effective increases to the right, and the reason for that is our calculation. We would say that Z effective, which equals Z actual minus the shielding. And I think that is so super confusing because when we talk about Z effective, it's like, all right, so that's the actual field that the electrons end up filling, and you're like, oh shit, there's Z actual, right? So anyway, Z actual is just Z, right? More or less, Z actual is Z for our atom. And so what we're doing as we go left to right across the periodic table, is Z increasing or decreasing? It's increasing, right? So plus 1 as we go left to right. What's happening to the shielding? Not much, right? Because we're not changing the number of inner electrons. And so if we're not really, there are some differences. Ultimately, we're not going to have identical values, but we're not going to see a huge difference in the shielding number here because we're not really affecting the inner electrons whatsoever. The valence electrons themselves can sometimes contribute the smallest amount of shielding, but ultimately what we're seeing is no change. And so as we move across the periodic table, what we see is that Z is going up each time we go left to right. There's nothing happening here, and so if more or less this value doesn't change, what's happening to Z effective as we go left to right? It's increasing along with Z actual, and so that's the trend. That's why we see atoms get smaller going right, because we're changing the Z actual, we're not doing anything to the shielding, and so the Z effective just gets smaller and smaller and smaller. Yeah?
Do you ever want us to calculate the thought dissociation energy?
I don't think we have any way to do that. Not yet. So actually that's going to creepy though. We will do that probably in the exam too. So, yay. Yeah.
When naming compounds, when do you use the prefixes and when don't you?
So, ionic compounds, make sure I remember what I'm doing here. So ionic compounds never use prefixes. Never, ever, ever. And the reason that they don't is ultimately it's too much information because we can already figure out how many there are based on the charges. So it's just unnecessary. We only use prefixes for covalent naming. And so anytime we have, for the anion, you're always going to name how many there are. So you'd say mono or di or tri. And I shouldn't say the anion because covalent, we're talking really the more electronegative element. So the one that comes second is what I mean to say. So the second element always gets a prefix. The first element always gets a prefix unless there are how many? One. And if there's just one, we just say the element, and that's it. So basically, easy way to remember it, ionic never, covalent always, except for the first element when there's one. Yeah. Yeah.
Are we going to need to know
No. You'll just need to, if that's one of the ions on the polyatomic ion sheet, it's just part of the name.
Okay.
Yep. I think permanganate probably on there. Yeah.
Based on what you said with the ML, there, I'm just wondering with the chart on the guidance exam, it says possible value of ML, so with the L is 2 and you only said -1.
Yeah, and so that's,
You only need to pick 1.
right, and so that's just to avoid me requiring you to write out 5 numbers, right? So yeah, if we've got a d orbital, that's an L equals 2, and so a possible value, there's 5 possible values for M sub L, give me one of them. Yep. Yeah, 50-minute exams, I gotta make it so you can go through pretty quickly. It's not very long. We get hour-and-a-half exams in Michigan. I like that a lot. It's fairer to you. Students are always like, ugh. But then it's more comprehensive, which means if you know your stuff, you're less likely to get like one problem wrong and have it really nail you. So I like longer exams. Fairer to you, ultimately. Yeah.
Is there any partial credit on like the longer
Yeah, absolutely. I wish I could give partial credit on every. I wish I could write the exam such that partial was available for every problem. Unfortunately, that would take me about 1,000 hours to grade. But absolutely, like the calculation-based problems, yeah. You know, if you mess up a unit, and it's the sort of thing I tell people that you'll see on the exam, just like last year's, you have to show all of your work, because let's say a problem's worth 15 points. If you give me the right answer, but you don't have any work there, I might give you 3 points for having the right answer. But for all I know, you just pulled that off somebody's exam. So, alternatively, if you had the entire thing set up perfectly and then had a calculation error, I'd probably give you like 12 out of 15 because you know what you're doing. So, you can't just put answers. Gotta show work for calculations. Yeah.
When we're drawing data structures, how do we know how many bonds
An element. And so it's just based on the number of valence electrons it has. So, you know, fluorine's in column 7. And so it's going to want to make 1 bond because if it loans out a bond, it can get 1 back to form 8. Oxygen is going to want to make 2 since it's got 6, so it wants to loan out 2 so it can make 2 back. So that's the quick and easy way to remember how many they want. Yeah.
For resonance structures, is that you only have to make those whenever there's like more than 3 atoms and more than 1 way to combine?
Say that again.
Like, you only make resonance structures if there's more than 1 way to combine?
Yeah. Yeah, specifically in cases where you can draw multiple closed shell examples.
But you'll tell us, like, draw a resonance.
Yeah.
Okay.
Yeah. Yep. Yeah. We didn't go into much depth on that, not as much. So I would not have a question on this upcoming exam quite like the last one on last year's exam, just because we didn't go into as much depth. But I figure you'll learn that in Orgo if you take Orgo. But it's just which is more stable, which would we expect to be more stable. So the more charge we have on something, the less stable it is. So that's why in the notes when we had some atoms that had like a +2 charge on it, that's not a very important contributor just because it's very high in energy. So that's one way to do it. It has to be closed shell. And then in worst case, where you've got to say 1 negative charge on an oxygen versus 1 negative charge on a nitrogen, which would be more stable? Which is the more electronegative element? Oxygen or nitrogen? Oxygen, and so that would be more stable. But again, we didn't go into as much detail, so I wouldn't spend too much time on that. Yeah.
Can you do a quick example of writing the molecular configuration?
Yeah. Let's see. Somebody pick an element. Calcium. Okay. So let's see. I don't like to write a lot, so we'll do some shorthand. And calcium's not too bad. So for calcium, we've got a situation where we've got. Let's see. What's the what inner electron can we abbreviate it? It's inner. I guess, yeah, argon, that one. All right, so we're doing calcium, And so what we would use, we'd say, well, argon, it's got those inner electrons. That makes this a lot easier. So then once we've got argon, we see calcium, it's got an atomic number of 20. Argon's got an atomic number of 18, so we need to add a couple of electrons. What orbital will those two other electrons go in? Yeah, so this would be 4s, and they would both go in that one since there's always only one s orbital. We could make this a little more complicated. We could do, say, let's do titanium. And so titanium, just like calcium, let's see, has an inner configuration of argon, and then we've got 4s2, and then we've got two more electrons, which will go where? Yeah, in the 3d. And if we draw out, if I ask you to draw these out, what they look like, of course, we'd have 2 electrons in 4s. How would we distribute the 2 electrons in the 3d orbitals? Yeah, they look like that, so we're never going to start pairing them up until we run out of empty orbitals. Yeah. Well, you know, we could do one of the f orbitals, but the thing about the f orbitals is those, as you move down the periodic table, the electron configurations start getting really wonky. So you'll see, like, as you go from like whatever that is to that, you might put that electron in a d orbital for reasons of I have no idea, other than it must be most thermodynamically favorable to do that. So, you know, I'm not going to have one of those on the exam, and in reality, they all buck the trend. They're weird. But in fact, I forgot to do this on Friday. There's a really cool periodic chemistry professor, really cool periodic table. I don't know if you guys have ever found this. If you simply Google periodic table, the first thing that comes up is dynamic periodic table. It's the coolest, like, even if you're not a chemist, it's really cool. So basically, it tells you a ton of information. You can click on it. It brings up the Wikipedia page for that element. And then you can click on, like, properties. You could do, say, like, radius. You could do density, heat, abundance, electron affinity, electronegativity. It's kind of cool. Anyway, this is what I do all day in my office. I just look at this periodic table. What was I going to do? I was going to do, let's see, orbitals. So this one's cool. So like as you go left to right, you can see the actual orbitals getting full. Remember that d orbitals like to dip down and still an s electron, and so as we go titanium, vanadium, we'll put one in the d orbital. And then what happens is when we go to chromium, we can see that 2 are now in the d orbital because we stole 1 from the 4s over on the other side. So that follows our trend. But then if you go down to the f orbitals, you see that as you go, well, that one's actually kind of normal and I don't know. Well, maybe it sees down here. Anyway, I don't know. It's weird. So we won't worry about the f stuff. But it's cool to be on a table if you ever, if you're bored. I don't know. Yeah. What else? Huh?
So do they only dip down when they want to have 10?
Or 5. So half full or full. So that's why chromium, with what we would expect to have 4d electrons, has 5. Probably the same for molybdenum, yeah. Not the same for tungsten, but again, it's because as you go down, things get complicated. I'm not ever going to give you anything that doesn't follow the trends that we learned. So, yeah. Over here, we would see copper and zinc have the same number of d electrons, and that's because copper steals 1 from the 4s because it can be completely full. So, yeah. Yeah?
For naming molecules, will we be told whether it's ionic or covalent, or just going to recognize?
No, it'll be up to you to recognize. The easiest way to tell if something is going to be ionic or covalent, don't worry too much about the second element. Look at the first element. If it's in the first or second column, or if it's a transition metal, it's ionic. These things do not really covalent bond, any of this stuff. The only thing is kind of like this diagonal line that runs right here, and only stuff at the top right of that will be involved with covalent bonding. So if your first element is over here, and we're never going to see one of these elements second because those are the least electronegative elements. So if it's this stuff, it's going to be an ionic compound. If your first element is this stuff, it's probably covalent. Yeah.
sorry, for the like transition metals, whenever you ionize them, is it you lose an S electron first? I thought I like read that.
Yeah, and so that's why +2 charges are so common with the transition metals. Is any of these, or at least, and there's the odd cases, but most of this stuff has 2 s electrons, right? And so as they ionize, as they become cations, they're going to lose their s electrons first, and since there's 2 of them, they go to a 2+ charge, and so that's common. And then we can start pulling off d electrons as well, and so there's a lot. Stuff like manganese, I mean, it has like +1, +2, +3, +5, 6, 7 are all common charges for manganese. So we'll do a demo with manganese when we get to that part. So as you go left to right, the radius that gets smaller, and we do also have increasing electronegativity. They're not really directly related, but the trend is they're kind of backwards, right? So we see a smaller atom like fluorine is going to be more electronegative than a bigger atom like nitrogen. Yeah.
If you remember this correctly, but in one of the problem sets, it showed like energy level goes from 5 to 4, and then next to it say comma, then 4 to 3, and it was asking for the wavelength. Is that just followed along the way with the 3?
Yeah, so we would just solve that using the Rydberg equation. The transition is 5 to 4, and so we would subtract. We'd have 1/4 minus 1 over 1/4 minus 1 over 1/5, and then we multiply that by the Rydberg constant and find the wavelength. Yep. Yeah.
So when you use the Roman numerals in the basic, is that for the transition column?
Pretty much, yeah. So the first 2 columns, you don't really need to use the Roman numerals, and that's because those elements, there's only really one charge that they're going to commonly find. So like potassium is always going to be plus, magnesium is always going to be plus 2. And so you can have, say, you can look at that. If you see those elements involved in an ion compound, you can look at that. You can use that as a source to figure out what your overall charge is, because you know that it's going to be that charge. The transition metals have multiple, and so generally, really all you see is the transition metals that you need to have Roman numerals with, because then there's multiple charges that can be.
So do you always use them for that?
With transition metals?
Yeah, there was one maximum problem. It was CnCrO4, and it said it was zinc chromate without Roman numerals.
Yeah, I mean, so you can figure out, even if it doesn't say, you can figure out what the charge on zinc is based on what the charge on chromate is, because it's got to balance out the chromate charge.
But when you're making it, is it like you don't always?
I don't know why that wouldn't list it. I would, because it's a transition metal, expect you to list it. Yeah, there might be some little rule I don't know, but I certainly don't expect you to know. So yeah. Yeah. So the easiest thing to do is just look at the column. So like sodium wants to lose an electron because it's in a closed shell, and so sodium is pretty much always going to have a plus charge because it really only ever wants to lose 1 electron. Magnesium is always going to exist as +2 because it needs to lose 2 to become closed shell, and that's pretty much we're never going to see magnesium +1 because if there's enough energy for it to become +1, there's probably going to be enough energy for it to go on and be +2 as well. The transition metals aren't a clear-cut case like that because of the way that s electrons get pulled before the electrons. So anything in the transition block can usually take on the charges. Yeah, so on the anion side, this stuff's only ever going to be minus because there's just no reason. Once you've got an electron configuration like argon, there's no reason to add an electron, right? You're not going to gain anything. You're no longer going to be closed shell. And so column 7 is only minus, column 6 is only -2, and then I guess you can rarely see nitrogen involved. Usually it's just column 6.
For the last question in the practice exam, which one was the best structure? Can you explain why, I don't remember the answer, but why which one was better than the other one?
Yeah, so we didn't go into as much depth on that topic, but what we've got is ultimately, if we add up the electrons here, we've got oxygen with 6, sulfur with 6, carbon with 4, nitrogen with 5. So we've got 6, 12, 16, 21, 22, 23, and then 24 from the -1 charge. So we've got 24 valence electrons. And so when we draw our structure, if we just distribute electrons, let's see, we've already used 2, 4, 6, 8, 10. I'm going to subtract, get rid of that. So what we could do is we've got 18 left. I'm sorry, we've got 14 left. And so we could put 2, 4, 6, 8, 10, 12, 14, which means all of our outer electrons are closed shell, but, all of our outer atoms are closed shell. The inner atom is not, and so we've got options. We could donate electrons from the oxygen, which would leave us with this charge. Let's circle them. Let's put that. Then we could donate from the sulfur, and so if we do that, we'll end up with this, where the oxygen is negatively charged. And then finally, we could donate from the nitrogen, which is going to leave both oxygen and sulfur negatively charged. Did that stuff just come out of midair? Okay, that's weird. And in this case, so we've got minus on sulfur, minus on oxygen. That's really weird. And then a plus on nitrogen. Okay, and so, again, we didn't go into that much depth, but we could definitely say that the one on the right's the worst because there's just so much charge, right? So this is bad. This is the worst one. And then we're comparing essentially a negative charge on oxygen versus a negative charge on sulfur. And so which one's more electronegative? Oxygen. So which structure is most stable, 1 or 2? It'll be 2 because that's where we've got the negative charge. So, you don't even need to know that much for the exam. My organic side took over last year and I went a little more in depth. So, yeah. Yeah.
On the homework, there was one, like the homework was due on Wednesday. There was one that there were several ways you could have done it. The website only accepted one. Is that like how it's going to work for resonance structure? On the homework?
So the homework, it might go a little more in depth than I will on the exam.
Okay.
So does the homework ask you for a best structure?
No, it said
Find the best structure?
no, it just said just draw the Lewis structure.
I'll just draw the Lewis structure.
Yeah, and we had several ways where like it was correct, but the one that is.
Yeah, I'd have to take a look at it. I don't know. On the exam, on this exam, you're going to know if I'm expecting you to draw resonance structures. So that'll be clear. In drawing structures, I'll either say draw the Lewis structure where there's only one possibility, or I'll say draw the resonance structures of the, yeah.
Also, the homework, they didn't specify sometimes whether they wanted formula or not. So it's like, I feel like this, if the formula is clear on the exam, it should be always.
So you can assume you always need to draw a formal charge on a Lewis structure. It's not a correct Lewis structure unless you have a formal charge indicated. Yeah. Yeah.
So we do formal charge even if the atom is neutral?
Well, if it's neutral, you don't have to worry about it. So basically, if there's a non-zero, if you have a non-neutral atom, you have to indicate what the charge is. Yeah. And I think I have that in the directions on the exam, so to be clear about it. Yeah.
When do we need to indicate bond polarity?
When I ask.
Okay, so it's like not a.
Yeah. talking about. So we say that the formal charge is equal to the number of valence electrons in neutral atom. And so that's just the atom. And so then everything over here to the right is going to involve the atom within the molecule. And so when I say minus lone pair electrons, that means when we look at the structure, we look at that atom specifically now as we have put electrons around it in the structure, how many lone pair electrons does it have then? And so then also the number of bonds that it's making now that it's in the molecule. So yeah, for the first one, we just look up on the periodic table and we can count how many there would be. And then for the second and third one, we look at how have we arranged the electrons, how many lone pair electrons does it have, how many bonds does it make. Yeah.
Can you explain the first statement in problem 5 of the practice?
Yeah. All right, so what we've got is the situation. So it's the energy required to promote an electron from n equals 1 to n equals 5, and hydrogen is compared to the ionization energy. And so you don't need to use that energy at all. You just need to know what ionization energy is. And so, of course, ionization energy is the amount of energy required to take an electron and just completely remove it from the atom, right? All right, so what we're doing is we're comparing that process, the removal of an electron, to the process of just exciting an electron from 1 to 5. And so essentially it's the difference between this case where we're going to excite the electron from n equals 1 to n equals 5, and so there's going to be some delta E. We're comparing that to the ionization energy, which is basically the equivalent of taking this electron and throwing it up out into space, right? It's no longer even in an orbital on the atom. And so that delta E is going to be a lot bigger than the delta E between 1 and 5. And so ultimately, we would say that the energy required to promote it from 1 to 5 is going to be quite a bit less than the energy required to promote it from 1 to infinity.
Is there going to be anything on test tomorrow that isn't on the practice test?
Oh, yeah, amazing. That's definitely,
Like, what?
So it's the equivalent of what's on the exam.
No, but like, what? Like, if this is a really good thing to study, I can't just study this.
Yeah, I mean, it is a good thing to study. And honestly, I think I did a pretty good job last year of it being pretty comprehensive, and then this year as well. You know, it's the sort of thing where, I don't want to give too much away, but, you know, maybe we learned a couple of trends for something. And so on last year's exam, I tested you on one trend, or tested them on one trend. And then this year, I'm probably not going to test you on that trend. I might test you on the other trend. And so I'm trying to, it's good, the concept, conceptually, obviously it's going to be the same. I just might think about other aspects of it than this. So. And it's the sort of thing where if, what's on the exam, it's, whatever we did over the last 4 weeks, it's all fair game. So, yeah.
So if you were in this class, if you had just gone to this review session,
Yeah.
what would you do afterwards? Before the test?
If I was in this class and I had looked over the practice exam and hadn't had any problem with that, I'd probably feel pretty confident going into the exam. If there were some things that I struggled with, I would probably focus on those things for the rest of the day. Make sure I had a clear understanding, work a ton of problems from, say, the online homework or just the textbook involved with that topic. I say this all the time. I could put only pretty much, I can ask you questions on the exam, right? And so if you've answered every question known to man on some topic, you're not going to be surprised by anything I put on the exam. So part of this is just triaging what you know and what you don't know so that you can spend your time and make sure you're focusing on the things you don't know as well. So, yeah, that's what I would do. Yeah.
Sorry, I'm being repetitive, but I was in here for the first 15 minutes of the session.
Sure.
Can
can you explain the first question in problem 5, like the top one?
Yeah. So what it is basically it's ionization. It's the one with ionization energy. So ionization energy is essentially removing an electron from an atom. And so if we excite an electron, we're not removing it from the atom. We're just moving it further away from the nucleus. So here's the situation where we would excite it from n equals 1 to n equals 5. And so that's got a delta E associated with it. The equivalent picture for removing it completely, meaning the ionization of that atom, would more or less, you'd have this electron that has just gone up to infinity, right? And so that delta E is huge compared to this delta E that's a lot smaller. And so that's how you do that one. Yep. Yeah.
In general, like, for that question, why would you excite the hydrogen molecule to a bond separate? Would that be like a share of another atom?
Well, I mean, all you've got to do is hit it with a photon that has that delta E, and then what you're gonna, I don't know so much about the physics behind it, but if you blast it with a photon that has that delta E, then you have the correct delta E to excite it up to here, and so it can happen. You know, it's like you shine light on something, and it heats up, right? Now, it usually doesn't heat up by a lot, right? But every time one of these, the light from these light bulbs hits something, it's heating up the surface slightly. And what that is you have atoms that are absorbing that energy, which means the electrons are moving up, and then they fall back down. But they don't emit light. Remember, we saw that only dilute gases emit light. What they do is actually they just vibrate a little more, which is what they heat.
And then, but like, if the hydrogen is that's that energy.
Yeah, it's in the ground state if the electron's as low as it can be. Yeah.
Thank you.
You're welcome. Yeah. Yeah.
Can you go over number 6 for me?
All right, so osmium is the densest known element with a density of 22.59. It's also not cheap, and so a 120 cubic centimeter sample costs $35,000. How many osmium atoms can you buy for $1? Okay, so we have a volume, we have a density, and we have a number value. And so what we could do is we could more or less, if we could find how much an osmium atom is per dollar, we've pretty much got it, right? So if we know that some volume of osmium costs this much, if we can figure out how many atoms of osmium are in that sample that cost 100 and whatever the value of 35,000, we know how much it is an atom per dollar. So essentially what we're looking for is atoms per dollar, and so we have 120 cubic centimeter sample. And so if we essentially want to get this volume into atoms, but we don't have a direct volume to atoms conversion. So we're going to have to use the density first. It's the only other thing we've got. We could use the density to get that into a mass. And so we could say that, well, we know that we have 22.59 grams of osmium for every cubic centimeter of osmium. So now we know what the mass of our sample is. And then, of course, what we could do is, if we want to go from a mass to a number of atoms, what would we do? First, what do we go through? What is the big thing in chemistry? Yeah, and so to do that, we have to get moles, right? So what we would do is we'd look up at osmium on the periodic table, because we know that we know how many atoms there are in a mole of something, right? We know how many anything there is in a mole of anything. And so if we can get this to moles, we'll know how many atoms we've got. Okay, so if we've got grams of osmium and we want to get moles of osmium, how do we do that? Yeah.
Wait, there's someone back there.
What?
Oh, I thought you've multiplied by 1 mole over 190.2.
Yeah, so we look up at the atomic mass of osmium. So it's 76 up there, so that's 190.2 grams per mole. And so here we would say we've got 190.2 grams of osmium will give us it corresponds to 1 mole of osmium. So now we've got the moles of osmium, and so if we've got it in moles, then we can convert to atoms. We'd say that in 1 mole of osmium, we have how many atoms? Yeah, so that's just Avogadro's number. And so now what we've got is the number of atoms, and so what we can take that is we can just put that over the overall cost of our sample, which was $35,000. And so what that will spit out as an answer in atoms per dollar. And so since it asks how many can you buy for $1, it's just whatever that value is. Yeah.
Tomorrow we can use a calculator.
Yes, I probably should have said something about calculators. Yeah, absolutely. I'll send out an email reminding people to bring calculators. Yeah.
Sorry, I did look at the cover sheet. Do we have to memorize the energy equals like H times C over lambda?
No, I think that's on there. I'm pretty sure that's on there. Yeah. I told you, right around an hour and a half, it starts to kind of figure out. Yeah.
Would it helpful to memorize the electromagnetic spectrum because of the questions like which one has the higher wavelength? Because I wouldn't have been able to like make a table like you did.
Yeah, I mean, it's fair game because it's in the notes, but I would not spend much time focusing on electromagnetic spectrum. You can do that in physics. All right, well, unless you have other final questions, I will see you all, not too bright and early, I guess 11 or 12 tomorrow. So good luck studying the rest of the night. I will get this posted ASAP.